Testing 1, 2, 3. Want to quick make sure this works. Okay. I'm gonna move my stuff up. So, probably not going to be doing as many exercises tonight. Just want to mainly read through cyclic groups, because permutation groups kind of cover all finite groups in a certain sense, and the Cosis and Lagrange's theorem is very general. Cyclic groups are a really good introduction to a lot of the abstractions about things, so I want to deal with cyclic groups first in kind of like an offhanded way. So, let's just get right into it. Cyclic groups. The group Z and Z sub n, which are among the most familiar and easily understood groups, are both examples of what are called cyclic groups. In this chapter, we will study the properties of cyclic groups and cyclic subgroups, which play a fundamental part in the classification of all abelian groups. 4.1. Cyclic subgroups. Often, a subgroup will depend entirely on a single element of the group. That is, knowing that particular element will allow us to compute any other element in the subgroup. Example 4.1. Suppose we consider the integer 3 in the integers, and look at all the multiples, both positive and negative, and 0 of 3. As a set, this is 3 times z is equal to 0, 3, negative 3, 6, on and on. It is easy to see that 3z is a subgroup of the integers. This subgroup is completely determined by the element 3, since we can obtain all of the other elements of the group by taking multiples of 3. Every element in this subgroup is generated by 3. Example 4.2. If h is equal to 2 to the n for all n integers, then h is a subgroup of the multiplicative group of non-zero rational numbers, q star. If a is equal to 2m and b is equal to 2n or an h, then ab minus 1 equals 2m, 2 to the negative n equals 2 to the m minus n is also an h. By proposition 3.31, which tells us whether a subset of a group is a subgroup, h is a subgroup of q star, determined by the element 2. Theorem 4.3. Let G be a group and A be any element in G. Then the set, we're going to call it Langle A Wrangle, since that is what the symbols are called in LaTeX, which is equal to a to the power of k for all integers k, is a subgroup of G. Furthermore, Langle A Wrangle, or we'll call it the cyclic group generated by A, is the smallest subgroup of G that contains A. Proof. The identity is in A, or the cyclic group generated by A, since a to the 0 is equal to e. If g and h are any two elements in the cyclic group generated by A, then by the definition of A, we can write g equals a to the m, and h equals a to the n for some integers m and n. So, gh equals a to the m, a to the n, equals a to the m plus n, is again in the cyclic group generated by A. Finally, if g equals a to the n in A, then the inverse g to the negative 1 equals a to the negative n is also in the cyclic group generated by A. Clearly, any subgroup H of G containing A must contain all the powers of A by closure. Hence, H contains the cyclic group generated by A. Therefore, the cyclic group generated by A is the smallest subgroup of G containing A. Remark 4.4. If we are using the plus notation, as in the case of the integers under addition, we write the cyclic group generated by A is equal to n times A for n in the integers. That is, we write n A is equal to A plus A n times. For A and G, we call the cyclic group generated by A the cyclic subgroup generated by A. If G contains some element A, such that G is equal to the cyclic group generated by A, then G is a cyclic group. In this case, A is a generator of G. If A is an element of the group G, we define the order of A to be the smallest strictly positive integer n, such that a to the n equals e, and we write the bar of A equal to n. If there is no such integer n, we say that the order of A is infinite, and write order of A is equal to infinity to denote the order of A. Example 4.5. Notice that a cyclic group can have more than one single generator. Both 1 and 5 generate z sub 6. Hence, z sub 6 is a cyclic group. Not every element in a cyclic group is necessarily a generator of the group. The order of 2 in Z mod 6 is 3. And the cyclic subgroup generated by 2 is the set consisting of 0, 2, and 4 as equivalence classes. Notice that for the cyclic subgroup generated by 2, we are missing 1, 3, and 5. This fundamentally will come down, in this case, as a brief preview, it will fundamentally come down to whether or not our generator is co-prime to the modulo we're taking the integers over. The groups Z and Z mod n are cyclic groups. The elements 1 and -1 are generators for Z. We can certainly generate Z sub n with 1, although there may be many other generators of Zn, as in the case of Z sub 6. Example 4.6. The group of units, U9, in Z9 is a cyclic group. As I said, U9 is 1, 2, 4, 5, 7, and 8. The element 2 is a generator for U9, since U1 is equal to 2, U cubed is equal to 8, U to the 5th is equal to 5, U squared is equal to 4, 2 to the 4 is equal to 7, and 2 to the 6 is equal to 1. Example 4.7. Not every group is a cyclic group. Consider the symmetry group of an equilateral triangle S3. The multiplication group table for this group is in figure 3.7. The subgroups of S3 are shown in figure 4.8. Notice that every subgroup is cyclic. However, no element generates the entire group. So for example, we have as a first subgroup of S3, the identity, the rotation by 90 degrees of rotation by 120 degrees, the rotation by 240 degrees. We have ID, and one of the reflections, ID the second reflection, ID the third reflection, and finally ID. Example 4.9. Every cyclic group is abelian. Proof. Let G be a cyclic group and A and G be a generator for G. If G and H are in G, then they can be written as powers of A. Say G equals A to the R, and H equals A to the N. Since GH equals A to the R, A to the S, equals A to the R plus S, equals A to the S plus R, equals A to the S, A to the R, equals HP, G is abelian. Subgroups of cyclic groups. We can ask some interesting questions about cyclic subgroups of a group and subgroups of a cyclic group. If G is a group, which subgroups of G are cyclic? If G is a cyclic group, what types of subgroup does G possess? Theorem 4.10. Every subgroup of a cyclic group is cyclic. Proof. The main tools used in this proof are the division algorithm and the principle of well-ordering. Let G be a cyclic group generated by A, and suppose that H is a subgroup of G. If H is equal to the identity element, then trivially H is cyclic. So, suppose that H contains some other element G distinct from the identity. Then G can be written as A to the N for some integer N. Since H is a subgroup, G to the -1 equals A to the -1 must also be in H. Since either N or N minus N is positive, we can assume that H contains positive powers of A and N greater than 0. Let M be the smallest natural number, such that A to the M is in H. Such an M exists by the principle of well-ordering. Since it's at least 1, and we know that 1 exists, so we can go down, but we can only go down finitely many times. We claim that H equals A to the M is a generator for H. We must show that every H prime in H can be written as a power of H. Since H prime is in H, and H is a subgroup of G, H prime equals A to the K for some integer K. Using the division algorithm, we can find numbers Q and R such that K equals MQ plus R, where 0 is less than or equal to R is less than M. Hence, A to the K equals A to the MQ plus R equals A to the MQ A to the R equals H to the Q A to the R. So A to the R equals A to the K H to the negative Q. Since A to the K and H to the negative Q are in H, A to the R must also be in H. However, M was the smallest positive number such that AM was in H. Consequently, R equals 0, and so K equals MQ. Therefore, H prime is equal to A to the K equals A to the MQ equals H to the Q, and H is generated by H. Okay, so basically a argument by principle of well-ordering, and a smallest argument where we use the smallest to ensure equality so that it's not a contradiction, or at least equality in the sense that one number is divisible. Corollary 4.1. The subgroups of Z are exactly NZ for n equals 0, 1, 2, on and on. Proposition 4.12. Let G be a cyclic group of order n, and suppose that A is a generator for G. Then A to the k equals E if and only if n divides k. Proof. First, suppose that A to the k equals E. By the division algorithm, k equals nq plus r, where 0 is less than or equal to r is less than n. Hence, E equals A to the k equals A to the nq plus r equals n to the a to the nq, a to the r, equals e to the ar, equals a to the r. Since the smallest positive integer m such that a to the m equals e is n, with r equal to 0. Conversely, if n divides k, then k equals ns for some integer s. Consequently, a to the k equals a to the ns, equals a to the n s, equals a to the s, equals e. Let me quick reread this just to make sure I absolutely got it down in my head, because this is also a review for me. Okay. Oh, this actually provides a proof for a previous exercise. That's actually pretty nice. So, Theorem 4.13. Let G be a cyclic group of order n, and suppose that A and G is a generator of the group. If B is equal to A to the k, then the order of B is n over d, where d is the greatest common divisor of k and n. Proof. We wish to find the smallest integer m such that e is equal to b to the m, and b to the n equals a to the km. By proposition 4.12, the proposition about the order above. This is the smallest integer m such that n divides km, or equivalently, n over d divides m k over d. Since d is the greatest common divisor of n and k, n over d and k over d are relatively prime. Hence, for n over d to divide m k over d, it must divide m. The smallest such m is n over d. Corollary 4.14. The generators of z sub n are the integers r such that 1 is less than or equal to r is less than n, and the greatest common divisor of r and n is equal to 1. Example 4.15. Let us examine the group z sub 16. The numbers 1, 3, 5, 7, 9, 11, 13, and 15 are the elements of z sub 16 that are relatively prime to 16. Each of these elements generates z sub 16. For example, 1 times 9 equals 9, 2 times 9 equals 2, 3 times 9 equals 11. It should be easy that we have every single element in this once. We generate the entire group by the, in this case, coprime element 9. Multiplicative groups of complex numbers. The complex numbers are defined as c equals a plus bi, or a and b in the real numbers, where I squared is equal to -1. There's a bit more subtlety, but for now it's just I squared equals -1. If z is equal to a plus bi, then a is the real part of z, and b is the imaginary part of z. To add two complex numbers z equals a plus bi and w equals c plus di, we just add the corresponding real and imaginary parts. I'm going to assume you've done complex stuff before, so I won't belabor the specific computational details. Remembering that I squared equals -1, we multiply complex numbers just like polynomials. Here's the moment where I pause to just say that will be important later. The product of z and w is, well, it's the following expression. Some amount of technical difficulties, so give me a moment to check this. Alright, things are coming back. Let me just make sure that the stream is properly up and running. Alright, it looks like we're almost back. Are we almost back? We got images. Oh gosh, this is very bad. Okay. So, how are your guys' day today? I hope, okay, yeah, it's coming back, I'm not gonna have to run the intermission again. Alright. So, yes, we defined the inverse of the complex numbers. Alright, the complex conjugate of a complex number, z equals a plus bi, is defined to be z bar equals a minus bi. The absolute value, or modulus, of z equals a plus bi is the absolute value of z equals the square root of a squared plus b squared. In the off chance that you haven't seen it, we basically set a complex number with the real part and imaginary part, create a triangle up to that point, and we take the distance of the hypotenuse. You may also hear this referred to as a norm. The norm of a complex number if you're working in certain like linear algebraic context. Example 4.16. Let z equals 2 plus 3i and w equals 1 minus 2i. Then z plus w equals 2 plus 3i plus 1 minus 2i equals 3 plus I, and zw equals 2 plus 3i, 1 minus 2i equals 8 minus I. Also, z to the negative 1 of 2 over 13 minus 3 over 13i, the absolute value of z equals the square root of 13, and z bar equals 2 minus 3i. There are several ways of graphically representing complex numbers. We can represent a complex number z equals a plus bi as an ordered pair on the xy plane where a is the x or real coordinate and b is the y or imaginary coordinate. This is called the rectangular or Cartesian representation. The rectangular representations of z1 equals 2 plus 3i, z2 equals 1 minus 2i, and z3 equals negative 3 plus 2i are depicted in 4.17. So we can just see this here in a similar way that I have written it down. Normally you would have coordinates indicating the 1i, 2i, or just the 1, 2 markings. Non-zero complex numbers can also be represented using polar coordinates. To specify any point on the plane, it suffices to give an angle theta from the positive x-axis in the counterclockwise direction and a distance r from the origin, as in figure 4.18. So we have this angle theta here, this amount of a unit circle off the just positive x-axis, and we have a distance r out that we go. We can see that z equals a plus bi equals r cos of theta plus I sine of theta. Hence, r is equal to the modulus of z equals the square root of a squared plus b squared, and a equals r cosine of theta, b equals r sine of theta. We sometimes abbreviate r cosine of theta plus I sine of theta as r cis of theta. To assure that the representation of z is well defined, we also require that 0 degrees is less than theta, less than or equal to theta, is less than 360 degrees. If the measurement is in radians, then 0 is less than or equal to theta, is less than 2 pi. This is because we can go arbitrarily high, and because theta loops, and the cosine and sine are periodic. As long as we are in the same respective place within each period, it will be the same. So we don't necessarily have a unique representation unless we restrict the domain like this. Example 4.19. Suppose that z equals 2 cis of 60 degrees. Then a equals 2 cosine of 60 degrees equals 1, and b equals 2 sine of 60 degrees equals the square root of 3. Hence, the rectangular representation is z equals 1 plus square root of 3i. Conversely, if we are given a rectangular representation of a complex number, it is often useful to know the number's polar representation. If z equals 3 square root 2 minus 3 square root 2i, then r equals square root of a squared plus b squared equals square root of 36 equals 6, and theta equals arctan of b over a equals arctan of negative 1 equals 315 degrees. So 3 root 2 minus 3 root 2i equals 6 cis 315 degrees. The polar representation of a complex number makes it easy to find products and powers of complex numbers. The proofs of the following proposition is straightforward and is left as an exercise. Proposition 4.20. Let R equal Z equal R cis theta and W equal S cis theta be two non-zero complex numbers. Then, ZW equals RS cis of theta plus psi. Example 4.21. If Z equals 3 cis of pi over 3 and W equals 2 cis of pi over 6, then ZW equals 6 cis of pi over 2 equals 6i. Theorem 4.22. Demoivre. Oh god, I hope that's how you say that. It's very French. Let Z equal R cis theta be a non-zero complex number. Then, R cis theta to the n equals R to the n cis of n theta, for n equals 1, 2, unknown. Proof. We will use induction on n. For n equals 1, the theorem is trivial. Oh gosh, thank you stream for lagging. Okay, hopefully it will come back on. If not, I'll just deal with it. Proof. We will use induction on n. For n equals 1, the theorem is trivial. Assume that the theorem is true for all k such that 1 is less than or equal to k is less than or equal to n. Then, z to the n plus 1 equals z to the n times z equals r to the n cosine of n theta plus I sine of n theta, r of cosine of theta plus I sine of theta, equals r to the n plus 1 cosine of n theta cosine of theta minus sine of n theta sine of theta plus I sine of n theta cosine of theta plus cosine of n theta sine of theta equals r to the n plus 1 cosine of n theta plus theta plus I sine of n theta plus theta equals r to the n plus 1 cosine of n plus 1 theta plus I sine of n plus 1 theta, as required for the inductive proof. Oh gosh. Oh, my internet is very much having a moment today. I'll keep reading and I hope it's not bad. Alright, example 4.23. Suppose that z equals 1 plus I and we wish to compute z to the 10. Rather than compute 1 plus I to the 10 directly, it is much easier to switch to polar coordinates and calculate z10 using de Moivre's theorem. Z to the 10 equals 1 plus I to the 10 equals square root of 2 cis pi over 4 to the 10 equals square root of 2 to the 10 cis of 5 pi over 2 equals 32 cis of pi over 2 equals 32i. Now this is the main thing that we've been building up to with this. The circle group and the roots of unity. The multiplicative group of the complex numbers, C star, possesses some interesting subgroups. Whereas Q star and R star have no interesting subgroups of finite order, C star has many. We first consider the circle group. T is the set of all Z and C, such that the absolute value of Z is equal to 1. The following proposition is a direct result of proposition 4.20. Proposition 4.24. The circle group is a subgroup of C star. Although the circle group has infinite order, it has many interesting finite subgroups. Suppose that H equals 1, negative 1, I, negative I. Then H is a subgroup of the circle group. Also, 1, negative 1, I, and negative I are exactly those complex numbers satisfying the equations z to the 4th equals 1. The complex numbers satisfy the equations z to the n equals 1 are called the nth roots of unity. Theorem 4.25. If z to the n equals 1, then the nth roots of unity are z equals cis of 2k with pi over n, where k is equal to 0, 1, all the way to n minus 1. Furthermore, the nth roots of unity form a cyclic subgroup of T of order n. Proof. By de Moivre's theorem, z to the n equals cis of n 2k pi over n equals cis of 2k pi equals 1. The z's are distinct since the numbers 2k pi over n are all distinct and are all greater than or equal to 0, but less than 2 pi. The fact that these are all the roots of the equation z to the n equals 1 follows from corollary 17.9, which states that a polynomial of degree n can have at most n roots, We will leave the proof that the nth roots of unity form a cyclic subgroup of T as an exercise. Yeah, we're not going to worry about fundamental theorem of algebra type results in this. A generator for the nth roots of unity is called a primitive nth root of unity. Example 4.26. The eighth roots of unity may be represented as 8 equally spaced points on the unit circle, figure 4.27. The primitive eighth roots of unity are omega equals the square root of 2 over 2 plus the square root of 2 over 2 I. Omega cubed equals negative square root of 2 over 2 plus square root of 2 over 2 I, w to the fifth equals negative square root of 2 over 2 minus square root of 2 over 2 I, w to the seventh equals square root of 2 over 2 minus square root of 2 over 2 I, which is the following. So one way to think about this is it's kind of a cyclic group on the angles, because like omega plus omega is equal to I, or omega times omega, the angle adds up to I, and you basically add angles together to go around this circle in unique ways. 4.3. The method of repeated squares. Computing large numbers can be very time consuming. Just as anyone can compute 2 squared or 2 to the 8th, everyone knows how to compute 2 to the 2 to the 1 million. However, such numbers are so large that we do not want to attempt the calculations. Moreover, past a certain point, the computations would not be feasible even if we had every computer in the world, in many cases in the universe, at our disposal. Even writing down the decimal representation of a very large number may not be reasonable. It could be thousands or even millions of digits long. However, if we can compute something like 2 to the 37,398,332 mod 46,389, we could very easily write down the result, since it would be a number between 0 and 46,388. If we want to compute powers modulo n quickly and efficiently, we will have to be clever. Let's check the footnote. The results in this section are needed only in chapter 7, which I remember is the result in cryptography, but we're still going to go through it anyway. The first thing to notice is that any number a can be written as the sum of distinct powers of 2. That is, we can write a equals 2 to the k1 plus 2 to the k2, all the way to plus 2 to the kn, where k1 is less than k2 is less than all the way to kn. This is just the binary representation of a. For example, the binary representation of 57 is 111001. Since we can write 57 equals 2 to the 0 plus 2 to the 3 plus 2 to the 4 plus 2 to the 5th. The laws of exponents still work in Z sub n. That is, if b is congruent to a to the n mod n, a to the r mod n, I think that's this, and c is equal to a to the y mod n, then bc is congruent to a to the x plus y mod n. We can compute a to the 2 to the k mod n in k multiplications by computing a to the 2 to the 0 mod n, a to the 2 to the 1 mod n, all the way to a to the 2 to the k mod n. Each step involves squaring the answer in the previous step, dividing by n, and taking the remainder. Example 4.28. We will compute 271 to the 321 mod 481. Notice that 321 is equal to 2 to the 0 plus 2 to the 6 plus 2 to the 8th. Hence, computing 271 to the 321 mod 481 is the same as computing 271 to the 2 to the 0 plus 2 to the 6 plus 2 to the k is congruent to 271 2 to the 0 times 271 2 to the 6 times 271 2 to the k. So it will suffice to compute 271 2 to the I mod 48, where I is equal to 0, 6, 8. It is very easy to see that 271 to the 2 to the 1 equals 73,441 is congruent to 329 mod 481. We can square those results to obtain a value for 271 to the 2 squared, mod 481. 271 2 to the squared is congruent to 271 to 2 to the 1 squared, is congruent to 329 squared, is congruent to 108,241, is congruent to 16 mod 481. We are using the fact here that a to the 2 to the n to the 2 is congruent to a to the 2 to the 2 to the n, is congruent to a to the 2 to the n plus 1 mod n. Continuing, we calculate 271 to the 2 to the 6 is congruent to 419 mod 481, and 271 2 to the 8 is congruent to 16 mod 481. Therefore, 271 to the 321 is congruent to 271 to 2 to the 6 plus 2 to the 6 plus 2 to the 8th mod 481 is congruent to all this. I'm just not even going to say it. The method of repeated squares will prove to be a very useful result when we explore RSA cryptography in Chapter 7. To encode and decode the messages in a reasonable manner under this scheme, it is necessary to be able to quickly compute large powers of integers mod n. So Sage, no. 4.4. Okay, reading questions before we hit our standard intermission. Alright, so let me just clear the whiteboard. Dang, okay, this was very quick compared to how it normally goes. Okay. What is the order of the element 3 in U20? So, what this will be, it'll be the integer n, such that the smallest one n, such that 3 to the n is congruent to 20. So 3 to the 1 equals 3. 3 squared equals 9. 3 cubed equals 27. 3 to the 4th equals, let me grab a calculator, is, wait, no, yeah, we're talking in the unitary group. So it'll be the number such that it's congruent to 1. So, calculator time. So, 3 times 3 times 3 times 3, 81 is equal to 81, which is equal to 4 times 20 plus 1. So 3 to the 4th is congruent to 1 mod 20, which implies that the order of 3 is equal to 4. Okay. What is the order of element 5 in U23? It's a similar computation. Find 3 generators of Z sub 8. So I guess we'll do that. So Z sub 8 is equal to Z sub 2 cubed. So 3, 5, and 7 will all be generators of Z sub 8 because they are relatively prime. Find 3 generators of the 5th roots of unity. Well, 5 is prime, so any one prime 5th root of unity will generate the entire group. Later on we'll show because there's an isomorphism between that group and the integers mod 5. Showed how to compute 15 to the 40 mod 23 effectively by hand. No, I think I'm good. We'll worry about that when we get to cryptography. Yeah, that was surprisingly fast for a reading. I think I'll just okay, I'll refresh one proof, which was very big, but I kind of just skimmed over. And then I will go into our normal intermission. Yeah. Oh yeah, never mind. Actually, I got that because it was G was a priori, I assumed a cyclic group. It actually wasn't a big thing that I thought it was going to be. Alright, so yeah, I guess before I go into some of the exercises, I'll go for a quick intermission to grab some coffee. So Alright, I got myself a nice cup of coffee. A relaxing time, I think. Let's switch back to the textbook. Alright, I haven't looked at any of these exercises, so whoever's watching, you and me are looking at them first, both. Okay. Prove or disprove all of the following statements. All the generators of Z sub 60 are prime. U8 is cyclic. Q is cyclic. If every proper subgroup of the group G is cyclic, then G is a cyclic group. A group with a finite number of subgroups is finite. Okay. There are some cool things. Alright, so first of all the generators of Z60 are not prime, because Z sub 60 is not a factorial. So it isn't the case that every number below it is already a divisor of it. Or actually, no. Never mind. What am I thinking? All the generators of Z sub 60 are prime. For example, let's think of a non-prime generator. So Z sub 60 is equal to 5 times... Wait, what's 60 divided by 5? Give me a second to figure this out. 60 divided by 5 is equal to 12. So 2 times 2 times 3 times 5. So 7 times 7 equals 41 is a generator of Z sub 60 because they're relatively prime. But it is not in fact the case that 41 is prime. U8 is cyclic. I would imagine so, but I'm not exactly sure. I'm too lazy to check because this is way too specific of the case. Alright, Q is cyclic. This is actually a very fun proof. So suppose P over Q generates Q, or generates Q star. Also, I should quick note that this is going to be obviously Q is not cyclic, but it's proving that. So suppose P over Q generates Q. P over Q times N is equal to Pn over Q. Hence, P over Q does not include P over QQ, which is in Q. Therefore, Q is non-cyclic. Okay. If every proper subgroup of a group G is cyclic, then G is a cyclic group. No. So, for example, I'll just leave it to the viewer to check. Z mod 2 times Z mod 2 is a obvious counterexample. Alright. A finite group with finite number of subgroups is finite. A group with a finite number of subgroups is finite. So, suppose the order of G is equal to infinity. Then G is equal to the union of G and G the subgroups of G. And because these are all, and there's an infinite number, yeah. Infinite number of subgroups. Because think about if only finitely many of these groups differed from each other. That means we had the subgroups represented by finitely many representatives of these cyclic groups. Would represent the entire group. The group would be a set-wise union of a finite number of cyclic groups. And each cyclic group would have to be finite. Otherwise, even within that cyclic group, you could find infinitely many subgroups, which would imply that the group G is finite. Gosh, it is weird doing many of these arguments informally, but I hope that argument comes across. Alright, find the order of each following elements. I'm way too lazy for that. List all the elements in each following subgroups. Nah, I want to try to find more proof. For a lot of these, it's late night. I'm much more into proofs than I am into computations. I'm kind of in that vibe. What are all grouping of the quaternion groups? Let's separate student right of subgroup. If A to the 24 equals E in a group G, what are the possible orders of A? Yeah, okay. So let's just do an example. If A to the P1, P2, all the way up. Alright, actually, wait, no. Here's a good way to put it. If A to the P is equal to E, then the order of A divides P. Right? Because suppose the order of A equals MP plus R. For R 0 less than R, strictly less than P. Then A to the MP plus R equals A to the E is equal to A to the MP plus R. That's A to the MP, A to the R equals A to the P of M, A to the R is equal to A to the R. And because R is the minimum number and 0 is less than or equal to this, we know that R must be equal to 0. Gosh, I'm very glad I'm refreshing on this book, because this book is it shows why the number theoretic methods are so important in proof theory. Alright. Find a cyclic group with exactly one generator. Can you find cyclic groups with exactly 2 generators? Also, yeah, the previous proof showed that the possible orders of A were these orders of A such that the order was a divisor. Okay. For n equals than equal to 20, which I'm not gonna worry about this. I forget if it's specifically a hard conjecture to prove or not with the way they stated that. And I'm lazy, so write the following numbers, complex forms for each of the following statements. This is much better for a complex analysis class, and I do have a complex analysis book I do intend to put on stream one later on. Listing graph of 6 roots of unity. Generators PQ have. I'll let P be prime and R be a positive integer. How many generators? Oh, these are actually okay. They're kind of related. So I'll let P and Q be distinct primes. How many generators does the PQ have? Okay. So I'll try this. So z of p q. So what it will be is that all numbers okay, let me think here. I feel like there should be a good expression. So like, for example, let's think of z6. Let's write out the Cayley table for z6, which is equal to z of 2 times 3. So we have 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 0. What? Oh wait, no, there's 0. I'm being dumb. 1, 2, 3, 4, 5. So it's 2, 3, 5, 0, 2, 3, 4, 5, 0. This is 4, 5, 0, 1. Oh wait, no, I should probably, oh yeah. Wait, let me think better. A Cayley table really isn't the best to investigate that. So we have 1 is obviously that case. So 1, 2, 3, 4, 5. We have 2, 4, 0. We have 3, 0. We have 4, 2, 0. And we have 5, 4, 3, 2, 1. So what I'm expecting there to be the amount of integers. So it's going to be fundamentally the same thing. It's going to be the amount of integers less than pq that are co-prime to pq. I just don't know if there's a certain like nice bound on that. Yeah, so let's think. So p times q. So we have q primes p. We have q primes p up to there, plus p primes q. So like, for example, 2 times 3. We have non-coprime numbers 2, 4, and 6, and 3 and 6. So we have 3 of these, and 2 of these, and we subtract the 1 where they're common. So we have p plus q minus 1 is the number of integers. Okay, is the number of integers that are coprime. So in this case, it would be 2 plus 3 minus 1 equals 5 minus 1 equals 4 that are coprime. So then we just take that and we just subtract it by pq minus p plus q minus 1. Does this factor in anything nice? So we have p q minus 1 plus q minus 1. Oh dang, okay. So we have p plus 1 q PQ minus 1. Oh, that's actually a fairly nice expression. I'm like, why is this problem in here? This seems really specific, but no, you end up working through the algebra and you get this very beautiful answer. Okay. So like, let's double check this with a few examples. So like for the example, this means z of 2 times 3 equals z6 has 2 plus 1. Oh shoot, I just realized also. Huh. Oh, that's wild. 3 minus 1 equals 3 times... No, wait, I did something wrong here. Let me go back. I think I did a piece of algebra wrong. Okay. We go back. Okay. So let's see where I went wrong with this. So we have p plus q minus 1. So we have pq. Yeah, this is where I went wrong. I was a dummy and didn't distribute. The number I got was a beautiful expression, just not the right one. Okay, so is equal to pq minus p minus q plus 1. Which is actually, I think it's 1 minus p, 1 minus q, right? Yeah, which is actually this expression, which is like just equally as nice. So let me be as conservative as I can, just in case I need to accidentally revive that. So for example, z mod 2 times 3 equals z mod 6. Let's do this with the right math this time. We have 1 minus 2, 1 minus 3, negative 1 times negative 2 equals 2 generators. Let's do this for another one, a more complicated one. So we have z mod 5 times 7, which is equal to z mod 35, which has 1 minus 5, 1 minus 7 equals to negative 4 times negative 6 equals 24 generators. All right, so all right, let p be prime and r in positive integer. This is actually useful for something called the fundamental characters of classification of finite abelian groups, or finitely generated abelian groups. So I will pay attention to this. So z sub p to the r with p prime, r is in z. We will have as our primes p1 or p1, p2, all the way up to p to the r minus 1. Yeah, actually, how did I list this? So it'd be p1, p2, all the way up to p to the r. We have to double count that, yeah, for the case of 1. So there are of these total. So it would be p to the r minus r elements which are not generators. So let's think. So like, for example, 2 squared minus 2 4 minus 2, 2, which is right because for z mod 4 it's 1 and 3. So let's think now to double check the work. Let's continue to be lazy and think of z mod 16, which is equal to z mod 2 to the 4. So let's think. So 2 to the 4. Also, it should be probably, I'm thinking, oh wait, is that just p to the r? They're p to the r total numbers, so it's p to the r minus p to the r. So it's just equal to r. Funky. There are that many total generators. Which doesn't seem right. We'll fix it later. So like for this, we have the elements from 0, 1, up to 15. This is taken, there's 1, 2, all the way up to r. So it should just be p to the r minus r. So yeah, that original expression was right. Oh yeah, I was jumping ahead. Yeah, there are them, so it was p to the r minus r. I was being dumb. So for this, 2 to the 4 has 2 to the 4th minus 4 equals 16 minus 4 equals 12 generators. All right. Okay. Prove that ZP has no non-trivial subgroups if P is prime. Well, okay, I won't prove this in writing, but the way to say this is that every subgroup of a cyclic group is a cyclic group. And if it has a proper subgroup, that means there's a subgroup with an order dividing the order of the group, which is strictly less than it, but P is prime, so that's impossible. And I'm just going to say this will have very important ramifications later. 26. 27. If G and H have orders 15 and 16 respectively in a group G, what is the order of G intersection with the order of H? I'm just not going to worry about that. And I think it's because 15, yeah, okay. Yeah, okay. I'm thinking it will be something close to like, yeah, 15 equals 3 times 5, and 16 equals 2 times 2 times 2 times 2. And because they have fundamentally different prime factorizations, they cannot correspond to any of the same subgroups, and as such, they like don't contain any elements in one another. Otherwise, such a thing like that would exist. Abelian element of group G, what is the generator of the group? I'm too lazy to think about that. Prove that Z sub n has an even number of generators for n greater than 2. Oh yeah, it's because for n greater than 2, Z sub n has a subgroup of order 2. And then there'll be an inductive based proof. Okay, there we go. First that G is a group and let A, B, and G. Prove that if A and the equivalence class of A is M and B is equal to N. GCD of M N equal 1. Oh wait, okay, this is picking up my attention. Show that the elements of finite order in G form a subgroup. Alright, so let G be obel. This is gonna be very important for later on. This is gonna be kinda hype. Okay. The set of elements of G and G, such that the order of G is strictly less than infinity is a subgroup. Generally also in higher level mathematics, torsion subgroups are very important. So like this is why I'm not skipping out on this. Like I shouldn't have skipped out on the centralizers earlier, but oh well, it's too late now. So if G and H is in this set, we'll call this set T, is in T. This means that G to the N equals E, H to the M equals E, which implies that G to the H to the negative 1 to the NM equals E, and since T is non-empty, obviously E is in this. T is a subgroup. And we need that abelianness to actually distribute over that product in a nice way. Let G be a finite cyclic group over N generated by actions, blah blah blah. Oh yeah, this is like a generalized argument that also, it's just generalizing what we see with the integers mod N. G is an abelian group. Prove that the subgroups here are exactly NZ. The generator is NZ, blah blah blah. G has no proper non-trivial subgroups, and G is a cyclic group. Yeah, okay. Yeah, okay, actually I'll prove this. I'll prove statement 37 because it's a kind of fun statement. So we're going to do this by contrapositive. So we're going to say, suppose G is not cyclic. Then there exists an element A such that the cyclic subgroup generated by A is not equal to G, which implies that A is a proper subgroup of G. Group of G. Also, like in the assumption, we assume that A is not equal to E. Let's put that as specifics for now. So yeah, if G is not a cyclic group, then G has a proper non-trivial subgroup. So by contrapositive, if G has no proper non-trivial subgroups, then G is a cyclic group. Alright, prove the order of element cyclic group must define the order of the group, which is nope. This theorem is kind of cool and kind of relates to like Sylow Theorem stuff, but not now. And then roots of unity stuff, which I'm not very worried about. 4.6 programming exercises. Write a computer program that will write any decimal as the sum of distinct powers of 2. What is the larger integer your program will handle? Course in number theory and cryptography. Second edition Springer. Alright, so I'm thinking, I don't know if I want to do a like preview of permutation groups, because permutation groups are like huge. So like let's kind of preview what we're going to be doing. Here, back matter, Galois theory, finite fields, vector spaces, lattices, polynomials, rings, the Sylow theorems. Let's look ahead to the Sylow theorems for a bit. I'll just probably be reading very casually until like whenever. Actually, if I want to be doing that, let me add a scene pure read along scene, which this should hopefully be a black screen right now. We add browser, add Chrome, and it will just be Chrome, so like we'll just drag it across like this. Hopefully that's centered. If not, my dearest apologies. Alright. So we already know the converse of Lagrange's theorem is false. If G is a group of order M and N, okay, so basically what Lagrange's theorem is that any subgroup of G will divide the order of G. The Sylow theorems do provide a partial converse for Lagrange's theorem. In certain cases, they guarantee us the specifics, existence of subgroups of specific orders. These theorems yield a powerful set of tools for the classification of all finite non-abelian groups. I'm wondering, wait, no. Instead of doing this, what if I just went on a category theory rant? Yeah, that's what I'm thinking. Okay, so. So I'm thinking for this, I'm thinking for the category theory rant. Okay. We're gonna be using the full power of the board. So when we describe the product of a group, we basically have, okay. Yeah, this will just be pure, just kind of like for my sake. So I'm not gonna go over any definitions. So you have G times H. And we have the projection 1 of G and the projection 2 of H. Now, is that the group that has that? So what this will be, if this is to be unique, such that we have for all E, for all Y, there's a homomorphism. If there's I2, one, there exists a unique F. I mean, it seems like it'll be something where it's like G, it will have to be the set of all GH with the normal group operation we already described. Because we can think of this externally described group already. The bigger question is how to design a coproduct, which I think is like the standard is like, it's called the free product or something. H. And we have the inclusion to a group like Z that gives us a unique this. So does this exist? So J1, J2. So like, for example, any information this will have some elements JG or J1G, J2H. So we can combine J1G, J2H. So yeah, what I'm thinking is we can at least describe a space that approximates it by not necessarily a coproduct. Because the main issue here is when we have G and H, we also have to be able to add at least finitely many of them together. So we'll have J coproduct with H, also coproduct with G times H, kind of? So basically, what we have is we're going to have elements in the form of J1G, J2H, J1G, J2 of H. And we'll define it so like J1G, J1G prime is equal to J1GG prime. Same thing with J2, and likewise component-wise for J1 and J2. And if we have two elements of J1 and J2 interacting, then we kind of have an implied identity on each of these. Wait a minute, so I'm wondering, can we just describe it as, because we have that zero element, right? So include, so we're thinking J1 sends G into G times H, which it's J1 of G equals G0. J2, oh my gosh, I think this is it. H, J2, G of H equals 0, H. And like, yeah. This looks like it's it. And to have the minimum number, we can actually describe this over a product of spaces. It's like the product of the group GI is the set product of GI is the set of all G in GI such that Pj of G equals 0 for all but finitely right. I guess the question then would be proving that this actually is a coproduct. Also, it's kind of weird from my experience in topology, at least, because it's kind of, it feels like it's more so flipped on its head in the topology version of this. Because in this version, G times H is a purely abstract group, while G star H, for lack of a better term, is a finite group, like a kind of almost finite related group, or a group where elements relate a finiteness condition, while there's no such condition on G times H. Because set theoretically there's something on G times H, but it's the opposite way for topology, where things can be very funky with coproducts in topology, which is why it's very nice for attaching, but it is relatively tame for products. So I guess let's prove it. So it's G, H, we have G star, H, and suppose we have some homomorphism to we set Z with, we'll call this lambda. We'll call this J1, J2. I1 or I2 I1. So we know that wherever G is sent, first of all, it should be obvious that it sends, we can always choose lambda that sends 0 to the 0. Now, first of all, we define lambda. We define, for example, lambda from G star H. Oh, okay, yes. This is where we need the finiteness condition on G star H, because that's the only way we can define this. We'll just worry about the case where it's G star H for now. So G star H 2Z is where, in this case, is this going to be G1, G2 is sent to, well, it's described uniquely, but yeah, G1, G2 equals I1, G, I2, G1, I2 of G2. And this is a well-defined description. And because only finitely many are non-zero, we have that this is a well-defined thing. Also, we know that because the arrows are monic, we're not going to have that G1 and G2 corresponds to different things in G and H. They're going to correspond to unique things. So it is properly well defined. Now the question is, the main thing here is the issue is that G1 composed with G1 prime, or you know what, yeah, I'm not going to write with the composition, I'm going to write with multiplication notation. G1, G1 prime to G2 prime is mapped to I1, G1, I2, or I1, G1, I1, G1 prime, I2, G2, I2, G2 prime. The issue here is that if Z is abelian, this works. Right, if Z is abelian, this works. So this construction, the coproduct is well defined when Z is an abelian group because we're able to rearrange this into its proper form. Thus that I1, G1. Because what I want to show is that I1. Actually, wait. Oh yeah, no. Because we want to show, what we want to show is that we want this to then be equal to I1, G1, I2, G2, I1, G1 prime, I2, G2 prime. Which this is only the case. This is only the case if Z is an abelian group. So this formulation of the coproduct, at least, is unique to abelian groups. I don't know if to put it in full generality, you might be able to put a stronger condition on this, a stronger free condition that might collapse down in the case of abelian groups. But I feel like I'm feeling like this feels right as a construction in the heart of what category theory is going for. So the question is, how do we modify this so that it works? Let's think about it. Let's think about it a bit harder. Maybe we can come up with a formulation. So we have J1, G, J2 of H. We need this to be equal to I1 of G, I2 of H. We know it's going to have to convert to something like this. Like, this seems like the only way to define it. But the main problem is that it's not a proper homomorphism on this. Because this would perfectly define the issue. This would perfectly solve the issue for the case where, like, the commutativity would be solved easily. It's like the only way we can resolve the commutativity. I'm thinking. Maybe more freedom of equality here? Okay, all I can say for certain, for now this seems like we need more structure to show the existence of something in the case of all general groups, which is something unique about category theory. When we extend our umbrella to a category above a category, we can actually have a more specific construction of the free group, as long as it satisfies this. But for now, all we can note is that this construction works in Abel. If it works in group generally, then it works in a way that it doesn't work in Abel. Yeah, I think that round was long enough. We had a cozy little time. We are preparing for, oh gosh, not this. Let me scroll way up. Oh, excuse me. We are preparing for, thank you, book, for being, oh god, good and not responding. We are preparing for, not the Sylow Theorems. Book, would you like to go up? Oh no, okay, it's having a moment. Give it a second. We're preparing for permutation groups, which, if you notice, goes from page 59 to page 74. Not an insubstantial amount, because our reading today was extremely short in comparison. Because permutation groups are, in a sense, the superstructure of all finite groups. But we'll get into that later. For now, I guess I'll clear out this horrible board and say, oh wait, yeah, I don't know if you guys actually saw that horrible board. Double check that I'm in the right scene. And say, thanks for tuning